Hi everyone, thank you so much for joining us today. We have a very special session and it is our 50th guest speaker session, so it is very exciting for me. We have with us very special guest speaker, Dr. Shaina Raza. Dr. Shaina is currently an applied machine learning scientist with a focus on responsible AI at Vector Institute of Artificial Intelligence, located in Toronto. She holds a Ph.D. in computer science, where her research centered around recommender systems and fairness in machine learning. Her research portfolio is diverse, covering areas such as recommender systems, ML fairness, public health equity, and ethical AI. Before her current position, Dr. Raza enriched her experience as a postdoctoral fellow at Public Health Ontario and the Dalla Lana School of Public Health. She held the esteemed position of CIHR HSIF award holder during the time. Over the years, Dr. Raza has made several contributions to her academic field. She continues her commitment to understanding and innovating at the crossroads of technology and societal welfare. Thank you so much for joining us today, and I'll pass it over to you.
Thank you very much, Ahmed. So I'm going to share my slides. So I believe my slides are visible, right?
Yeah, we can see.
Yeah, thank you. Hey everyone, thank you very much, Anis, for inviting me and introducing me. So today I will be presenting our research on mitigating bias in large language models while retaining context. So this research was conducted at Vector Institute in Toronto, Canada. And in this presentation, I will walk through the key aspects of our research, including the motivation behind the work, our methodology, the results, and the implications of our findings. So Ahmed has already given my introduction just briefly. I am applied machine learning scientist, responsible AI in Vector Institute for AI in Toronto. And my specialization is in recommender systems, fairness in machine learning, and responsible AI. You can contact me at my email address, shaina.raza@vectorinstitute.ai, and you can connect me otherwise on LinkedIn. First, I will talk about the motivation behind this research. So machine learning gives computer the ability to learn without being explicitly programmed. This concept was first introduced by Arthur Samuel in 1959. This is foundational to our research. So by that, I mean to say that key to any successful machine learning or AI solution lies in the quality of data, number one, and the algorithms used. For example, on the right side, you see that this is a typical machine learning pipeline. We have the data. The data is used to train algorithms, to build machine learning models, and finally, we get some AI solutions. But hold on, they are hidden biases. Mostly, we are not aware of that. So these biases can originate at various stages of the AI pipeline. The first kind of the biases that you see, irrespective of the AI, these are the systematic biases. They exist in our culture, in our society, and it is from the beginning of the history of the humankind. These systematic biases are then creeped into the data. They become data biases. Those data biases then creep into the algorithms and machine learning models. They become algorithmic and machine learning biases. And finally, what happened, we have a solution that is highly biased, but most of us are not aware of that because we just want to build the solutions. So this is a motivation for this research. In the next two slides, I will present some reality checks. For example, this slide, it presents the findings from the Gender Shades project. The link of the project is given here. So you see, basically, these bar charts display the accuracy rates of different algorithms for different demographics. The results indicates a significant disparity in the performance. For example, the algorithms, algorithm A, B, C, D, and E, they show the lowest accuracy for darker skinned females, while the lighter skinned males consistently achieve the highest accuracy rates. So this is something that we should never want to have this kind of solution. In this reality check too, you see that how racial biases in the face recognition technology is used by the law enforcement. So basically, this map indicates that certain racial groups, for example, Black and Hispanic communities, are frequently more targeted than white and Asian and others. So these are some of the concerns we must consider when making the machine learning models. As I mentioned, bias is as old as human civilization. It has been among us throughout the human history. Broadly, two type of biases, I will say: the human biases, which exist in our society, we also call systematic biases, and the algorithmic biases. So algorithm bias is basically a prejudice in the favor or against one person, one thing or group that is manifested in the AI systems, and it lead to the unfair outcomes. For example, if you're making a recommender system, you're making a classification system, you are working in the finance department, you're making a system that makes some decision on the mortgage or some of your assets. So if the algorithm is biased, data is biased, what happened? Chances are the outcomes that are produced will also be biased, and somebody will definitely be impacted because of such algorithms. Now, what is bias? Bias is a complex concept. It has many facets. For example, you might have heard about the bias in bias variance trade-off. That is simply something like which balance model complexity and prediction accuracy. You might have also heard about the inductive bias, which are basically assumptions an algorithm make to generalize data. So while some bias are useful, they guide the decision. However, in this particular work and presentation today, I am going to focus on those biases which lead to the discrimination, and I will also talk how to mitigate them. Some of the terminologies that I will be using in this presentation is bias in ML. I already defined these are the skewed errors in the algorithms that lead to unfair outcomes. Another very important term is the protected groups. So basically, in the science of or in the subject of machine learning and fairness, protected group refers to individuals or group which are identified by certain attributes like based on race, gender, age, disability, social status. Protected group has further two subgroups: the privileged group, the people or the group of the people who are at systematic benefit. For example, normally the male in our society, they are considered to be privileged, and unprivileged group, those people who are at the disadvantage. For example, normally people from certain religions, race, or normally the female in terms of the hiring processes, they are at the systematic disadvantage in most of the societies, not always. And then there is fairness in machine learning and ethical AI. These are the sub branches of machine learning. And basically the goal of both of them is that the AI systems or the machine learning models, they should adhere to the moral principles of the humans. So that is also the focus of my research and also the focus in this presentation today. So based on this motivation and context, I'm going to present our recent accepted paper, MBIAS, mitigating bias in large language models while retaining context. And my co-authors, Ananya Raval and Veronica, they have worked with me on making this model and the paper writing. The paper is available on the archive, and it is recently accepted in VASA in ACL 2024. Introduction. Before I go into the details of the introduction, let me define a large language model. You might have heard this word many, many times, maybe in your LinkedIn post, maybe in your in your news subscriptions, research papers in your universities or the production industry. So this is a very overrated and like it is too much used word these days. So what exactly is a large language model? It is simply a very, very large model with billion of parameters and many, many layers. So these models are trained on diverse data sets from the internet. They can be NLP-based models, which is the focus in our work. They can be computer vision models, or they can be multi-models. For the sake of this work, I will be only focusing on the NLP side of the large language model. If you recall the Google BERT model, that transformer architecture, so basically that is the backbone of the large language models. I don't mean to say that all these large language models are made from the BERT model, but the concept of the self-attention has been used in all of these. So largely the language models, they can be categorized as transformer models, for example, BERT, encoder-decoder models, for example, T5, some multilingual models. There are also many, many kinds. And the models that are more in fashion, they're autoregressive model. So autoregressive models are basically those which generate text by predicting the next token based on the previous content. So they also have like subtypes. One of them is the instruct models. Instruct models are those which work based on the prompts. So in this research, I will be focusing more on the instruct models. Now the thing is that LLMs are also obviously part of AI and machine learning. Biases do exist in the LLM outputs also. How do you see in LLM biases in LLM outputs? For example, they might describe a nurse as always female. They may link certain races to crime. They may focus on cities over the rural areas. So these are the biases that do exist on the LLMs, and there have been extensive research on that. And why these models are biased, the reason is that they have been trained on the data which has systematic biases. So that's why those biases have been a part of these LLMs also. There are many bias mitigation methods. I will cover shortly in the literature review slide. I mean, the links I have given, one can always read. So basically, the goal of all these bias mitigation method is to produce a version of the text that is free from the biases, or that is a benign version or neutral version of the biased text. However, what happened when we try to debias the text? So often there is some loss of information. This means at the cost of getting the inclusivity or fairness, we sometimes lose the actual meaning of the text. Let me give you some example. So in this one, you see like it's a people from small towns are not as open-minded as those from the big cities. So basically, like when we debias, we get a very nice benign version. For example, the level of the open-mindedness, and we are very happy that this is good. It's really appreciated. But if we go further, let me give you more example. So in the first example, it's say older employees are often resistant to change and new technologies. When we debias using some big LLM, what happened? We get the version individual openness to change and new technologies very widely. So did you notice that we get the inclusivity? However, we lost the age-related information, which could have been used for something like for making some decision. Similarly, in the second example, it says women in their 30s are more likely to take maternity leave. While deep biasing, I lose two pieces of information, the gender information and the maternity focus. So there is a trade-off. At the cost of inclusivity and fairness, we lost some information. And this is a situation we never want to have. And that is exactly the focus of the MBIAS. We want to debias, produce a version of the dataset that is benign, very nice, and neutral. However, at the same time, we don't want to lose the key information from the text. So here I talk about the objective of our MBIAS paper and this project basically. The goal is to develop a framework that address bias and toxicity in LLM outputs while preserving the content and the context. The key contributions of this work is a dataset preparation, introduction of MBIAS, which is a LLM instruction fine-tune model, and accessibility. It means we have made our dataset, our model, the fine-tune MBIAS model, and our code available for the community for use and reproducibility of the research. In this work, we try to address the research question that how can bias in LLM outputs be mitigated without compromising the integrity of the generated content. So in the state of the art, there are many methods. For example, diverse training data, adversarial debiasing, bias-aware methods, post-processing, red teaming, lately prompt engineering. I'm not going into the details of each and every because the links are given and there's a very massive literature available. Also, we have mentioned many of those works in our paper also. But broadly, we can categorize all these methods into two. That we say one are the traditional methods and one are the more state of the art or the latest method related to LLMs. In the traditional debiasing method, we observed the embedding space methods were the most popular. So what happened in the embedding space methods? We have some tests like VEAT and SEAT, and there are different tests. Basically, we try to debias the word embeddings. So this was something pre-BERT model. And after the BERT models, and lately when we have so many LLMs now the techniques are much changed. Prompt debiasing has been very popular technique. Like there are different ways we can devise the prompt to, for example, mitigate bias in the LLM outputs. There are a lot of techniques available. And there is another technique, which is instruction fine-tuning technique, the last one. So in instruction fine-tuning technique, we will be using the prompt, but we will be doing the fine-tuning. In our work, the focus is on the last one, the instruction fine-tuning technique that I'm going to mention in the next few slides. Methodology. So in the methodology, I will talk about our dataset construction, our MBIAS model, and inference. So our methodology can be defined as a pipeline with the following components in a very simplistic manner. First, we start with the corpus construction, where we collect the data. Then we have three models in a row. The model one, in which we use an LLM as an annotator, we get the ground truth levels. Once we have the annotated data, then we use the second LLM, which is our MBIAS model actually. It is an instruction fine-tune model, which play the role of a debiaser. And then we have a third model, LLM as a judge. So basically, whatever the outputs we have got from model 2, another model want to check it whether those new outputs, they are benign, or they basically whether they address a research question that reducing bias and toxicity while retaining context. Because we have so many LLMs in a row, it's very much important we should have a human review. So we have a team from different demographics and cultural groups and experts. So we made a team, and they oversee all the process. For example, they see the annotation process, they see the debiasing process, and they also evaluate the LLM judgments. So human review process has been an integral part of our pipeline. This is basically the architecture that we have shown in the paper. This is exactly the same figure that I have shown you in the last slide. It's just like presented in a more technical way. So you see, like, we have a data layer, and then we have a training layer, and we have the inference layer. Now I will explain the data layer. Data set. So our data set is basically sourced from our earlier bigger data set. The details of that big data set is available in this paper, Beats Bias Evaluation Across Domains. So this dataset you can access from this following link. It is also open for community use and research, and it is open. I mean, it is accessible, and the details are in this paper. So this big dataset has around 3.7 million records, and it covers many aspects of the bias. For example, in this column, in this table, you see it covers, for example, ageism, body shaming, climate change, lookism, linguistic, lifestyle. There are many aspects of the biases it is covering. So for this particular project of the MBIAS, what we did, we took a sample from this big data set. Our filtration criteria was that each piece of text that we pick should be above 250 words, and it should be covering at least 5 or 10 of pieces from each of the aspect. So we should have coverage from all the aspects from our bigger data set. This original bigger data set has been labeled for bias, toxicity, and sentiment. However, these are not the labels that we need specifically for this particular work. Those are the more classification tasks. What we need for this debiasing for our MBIAS work, we need the ground truth labels, which are basically the debiased variation of the biased text. By that, it means like our 8500 records, they're all, we consider them as biased. They are like, you can consider them as a rows or data frame. And the task is to create a debiased variation of each piece of text corresponding to that. So those debiased texts that we produce, they become our ground truth label. So in order to produce the ground truth labels, the benign or the debiased version corresponding to each text, we use our model 1. In this model, we use the LLM as an annotator. Why we use this? There is a motivation. Recent models or recent research has shown that models like GPT-4 can outperform even crowdsourced workers. Some big LLMs like Llama, Mr. Cloudy, they can annotate even up to human level accuracy. So it means we can rely on the LLM to annotate data for us. It is more scalable approach, and also it is considered, according to research paper, more accurate than the crowdsource workers. So for this task, we use the GPT-4, which is a very robust LLM as in the annotator role. So basically what we did, we give it the biased text, some prompt with few shots, and ask it to produce a debiased or benign version of that. After we get these ground truth labels, our team, the reviewer team, they basically review the quality of the debiased text. How they did, basically, we divided the debiased text among our team members, and each of them go through each of the sentence one by one. And if there were some discrepancies, some issues, they fix the issue on the spot. If there is more conflict or something, then a third person come and we try to resolve the issue. The goal of this all human in loop is that to maintain the reliability and credibility of the data. So our data set is in instruction data set format. I will explain shortly what are the instruction data set. And at the end of the annotation, our data set look like it's an ID, original text, which we consider most of them are the biased sentences, and the benign or the debiased version of the text, which will serve as the ground truth label. Instruction data set. So as I mentioned some slides ago, that these are the different language model if you see this chart. And we are focusing on the autoregressive models, for example, Llama, GPT series, and decoder-only models, basically. And it has one of the model, which is the instruct model. So if we want our, if you want to fine-tune an instruct model, our dataset must be instruct dataset. So basically what are instruct dataset, as I mentioned, this is the specific format of the data in order to fine-tune the instruct-based models. And they have the format like instruction, which is a natural language prompt specifying a task. In our case, this is a debiasing task. Input, in our case, the input is the biased text, and output, in our specific case, this one is the ground truth label. There are different instruction dataset formats available. For example, alpaca format from Stanford, ChatML format from OpenAI, this instruction input output format from Hugging Face, and simple question answering format. In our work, we convert our data into two formats, alpaca format and the Hugging Face instruction input output format. So how it looks, the instruction dataset, you see there's a system message in which we specify you are a helpful assistant. Then there's an instruction. So instruction is the task that you're saying to LLM to perform. For example, LLM as a, like we have said that, okay, devise this text, make it free from demographic biases. We can give as long as we want, it depends on the task. We can use zero shot prompting. We can even give some demonstration, some examples. We can even give chain of thought prompts. It depends how you like to take this. So this is a like very general look of how our instruction dataset format look like. So once our dataset is ready, so we make sure that it comply with the FAIR data principles. If you want to read about the FAIR data principle, this is one of our recent paper from Vector Institute. So the idea is to make the dataset number one findable. So definitely we have made it findable. We have uploaded it on the Hugging Face and it is available for everyone to use. Accessible, we have stored it in the format, for example, Crescent format, CSV format. The idea is that to make it accessible with clear usage licenses. Interoperable, this is very much important. So as I mentioned some slides ago, that a typical NLP dataset look like we have the ID, we have the biased text and the debiased text. You cannot use that exact data format, traditional NLP format, to fine tune an instruction model. So there is an intermediate step, which is in which we have to convert that into instruction format. So in our case, we have converted that into the OpenAI ChatML format, Hugging Face format, and alpaca format. So that's why we claim that our data is also interoperable. And finally, reusable. We have made this all research and data and code available for the community, so they can always add on the top of that. By this point, I have covered the first layer, the model one, the data layer. And now I move to the model 2, which is the second model, MBIAS. So before going into the fine-tuning details of the MBIAS, I want to tell that the backbone of the MBIAS model is Mistral 7B instruct model. We choose to work with the instruct models over the non-instruct version because we wanted a very conversational style of model in which we can play with the prompts, and then we can always fine-tune, or even some people can prompt tune it. The common hyperparameters for this model are given here, and all the details are available in the actual websites. If you open this link for the Mistral AI, so you will notice that there are many other modelwares for the instruct kind, even like version 0.3 and some other models. So because we have made our code available, anyone can just change the model path and maybe tiny 1 or 2 hyperparameters, and they can retrain it with another model, and they can get the same performance boost or even some better coverage of the bias aspects. Why we choose Mistral? We had also earlier used many other LLMs. For the Mistral model, according to its paper, this model has been highly fine-tuned for the safety. So if you see this link, I have given the image source. So without guardrails and with guardrails. So guardrails are basically referred to predefined rules or mechanism designed to ensure that the model outputs are safe, ethical, and appropriate. So Mistral model and even the Llama model, they have been highly fine-tuned for safety with guardrails. So what we did, we took this guardrail highly safety fine-tuned model and added another layer of safety, our debicing layer, to make it work for our specialized debicing task. So that was the motivation. As I mentioned earlier, that we are using the instruct model, so you can even change to some non-Mistral family. For example, something from the Llama, some other instruct model. Most of the things will remain same. You can always plug and play with the prompts. So in this slide, I will explain the instruction fine-tuning process of the MBIAS. So in this model, basically, we have instruction fine-tuned a large language model to act in the role of the debicer. So as there are 2 important steps and 3 important steps. The third one I will cover in the next slide for the instruction for fine-tuning the MBIAS model. As I mentioned, the backbone of the model is the Mistral 7B instruct model. You can always change to other model. So the first step is to convert the data into instruction format that we had already done, and we had even made that available for the community, so they don't have to do. And then the second step is to create training example. Each training example consists of a pair of the biased and the corresponding debiased text. We have used parameter efficient fine-tuning, which is a method of fine-tuning pre-trained models by updating only a small subset of the parameter. Why we use parameter efficient fine-tuning? Because we know that these large language models are very, very big. Many of the researchers may be hesitant, or even people working in the production, they are hesitant to use it because of the large size of this model. So it is a good technique that you can save a lot of compute by using the parameter efficient fine-tuning. In particular, we have used quantized language model optimization with low rank adapters, which is QLoRa techniques for parameter efficient fine-tuning. The idea of the QLoRa technique is to decrease memory and compute requirements. So in our work, we have used the 4-bit normal float quantization, double quantization, and paged optimizer. In our code, all the optimization, parameter efficient fine-tuning, and QLoRa hyperparameters are given. If you want to read more about this particular technique, so this is the original paper, the link I have given here. So by the end of our fine-tuning, parameter efficient fine-tuning process, what we get the adapter models. Adapter models are basically small trainable modules. These are very lightweight components that we get after parameter efficient fine-tuning. Compared to the extra original model weights, for example, the Llama or the Mistral, which are in GBs, the adapter model will be very, very less weight. So these models can be usable for like training. However, what we did, we merged the adapter model with the original Mistral model, and then we produced MBIAS So basically, MBIAS is just like a duplicate of the Mistral model, but with an extra layer of fine tuning, and which will act as a debiaser. And we have made this model available for inference to the community. So basically, I just wanted to show the link that where we have made available. So if you go to the link of the MBIAS, which is also given in the paper, so you will observe that the model weights of the MBIAS are just like the original bias, and it is readily be usable for production as well. The adapter models have been added because we don't want to give this kind of headache to the people that first they find the original model weights and merge it. We have done this from our end. Model training configurations. So these are very important configurations. I will define some of the important hyperparameters here. The batch size you observe, it is 8. Like most of us are already working in deep learning and even machine learning, we use batch size like 32, 64, 128. However, in this work, we have used 8 batch size, which is very, very less. Why we use? Because we want to avoid the cooled out of memory issue. I suggest when you use our code for fine tuning, or like if you run exactly like this, and if you stuck in this error code out of memory, you can even reduce the training size to 4 or even 2. That's totally fine as long as it will give you the same performance, but it will have less compute. The training epoch is 2. So normally in typical machine learning, other models, language models and deep learning model, we use many epochs and some early stopping. We also did this kind of like experiments. What we have observed that after 2 epochs, models started to overfit. This is exactly the same finding you will see in the Llama 2 paper or Llama 3 paper and even Llama Guard paper. So this is also our observation. So we just in the final run we give the 2 epochs and save the adapter model weights. So by this point, I have covered the data layer, the training layer, and now I will briefly tell about the inference. This model is available on Hugging Face. So these are just 2-liners. You can use it. What you can do with these 2-liners gives your data frame, your bulk data, and it will give you very nice benign version, neutral version corresponding to each of them. I will show you some examples shortly. The third model that we use is the LLM in the judge role. So an LLM as a judge is just like a decision maker that uses its vast amount of knowledge and information to give opinions or answers or judgments. In this work, we used GPT model again as in the judge role. And the idea is to basically judge the outputs produced by our model to the MBIAS model. And our exam taker model is the MBIAS, which is being simulated by the judge model for certain outputs and using different prompts, and to check whether it is addressing a research question or not. By that I mean whether the output from the model 2 is free from bias and toxicity, and whether it is retaining knowledge or not. So that's the role of the LLM judge. Now I will talk about results, and first I will briefly talk about our experimental setup. I think this is important because if you want to replicate this code or add on the top of that some metrics and results. So for experimental setting, we use a single A100 GPU with 4 CPU cores. Our training time was 50 minutes for 2 epochs. As I mentioned earlier, that over 2 epochs, it was leading to overfitting, so we stopped here. And the carbon emissions of our fine-tuned model, which is parameter efficient fine-tune, was 0.21 kg carbon dioxide units, which is considered to be very, very low compared to some of the big models. For example, the Llama 2 model, it produced 31.33 tons of carbon dioxide. And recently, Llama 3.1 was released yesterday. So it was mentioned in the model card that they have carbon emissions of 11,390 tons, which is too much. And which is fair because those are the pre-trained models. But I'm just mentioning our model is a fine-tuned model, and it is a parameter efficient fine-tuned model. So we just had 0.21 kg of carbon emissions. We can even further reduce that. For the evaluation data sets, we had 2 data sets. One is the in-house test set, which is derived from our training set, and the out-of-distribution data set. For the out-of-distribution data set, we have used the Toxygen data set, which has 13 demographic groups, basically minority groups. So for the evaluation, as I mentioned earlier, we use LLM in the judge role, and we give different prompts to that. And we want to evaluate MBIAS output for bias, toxicity, knowledge retention, faithfulness, and answer relevancy. The mathematical definition of these metrics are given in the paper as well as in this link that I have given here. But I can briefly tell you that what these metrics means. So bias and toxicity simple means they measure the presence of the bias related to gender, racial, political bias, toxicity, hate speech, offensive sentences, the presence or the frequencies of these things in the LLM outputs. A lower value of bias and toxicity is appreciated and considered the best case. The knowledge retention, faithfulness, and answer relevancy, higher values are appreciated. So basically, knowledge retention is something, it's in a very simplistic manner. I can give one example. For example, if I if I want to see that whether it is able to retain the factual information, like for example, if I say that what is the capital of France, so if it give me something wrong or like totally different or out of scope and start suggesting me a different kind of the outputs, it mean I'm not able to retain the knowledge, faithful, and answer relevancy. As I mentioned, these metrics they are very subjective metrics themselves. So in our case, for like how they are being used, the details of them are given in the paper. But for example, we wanted to check whether while debiasing, our model is able to retain the previous context or the knowledge, just like the example I have given earlier in the slides, that whether it has not lost the information related to specific gender, which is also called the hard debiasing, or for example, maternity focus, or these things. So we want to retain this information, and at the same time, we want to reduce the bias and toxicity. So we have used two kinds of the baselines, base models, Mistral 7B instruct vanilla model 0.2 and Llama 2 7B chat models. Both of these are instruct models, so we use because our MBIAS is itself instruct model. We have given then just one prompt to check the debiasing. Then we have the prompt tune models. So basically, prompt tuning is also known as prompt-based learning, which involve designing prompts or input templates that guide the pre-trained model to produce the desired outputs. So in that, we basically used some prompts with in the prompt template with some demonstration. The idea is to check these base models with some additional template for the debiasing purpose. And both the baselines are compared with our instruction fine-tune MBIAS model. Our evaluation scheme is that first we evaluate all these metrics on the original text as well as the ground truth labels. The ground truth label is the debiased text that we produced earlier using LLM as an annotator. And the post-debiasing is that we use all these baselines I mentioned in the last slide. We debias the text, and then we check again the presence of bias, toxicity, knowledge retention, and all these things. We, other than the quantitative analysis, we also perform the human evaluation. So in the human evaluation, basically what our reviewers did, they see the output, they gather the output of the MBIAS on a totally unseen data set. And they basically rate those samples using Likert scales on 1 to 5 for content neutrality, inclusivity, respectful interaction, and the output length. So these are the main results. This table is exactly present in the paper. If you see here, on the left side, these are the models. And if you see horizontally, the two important pieces of information, the pre-safety intervention and the post-safety intervention. Pre-safety means nothing have been debiased by any model. It's the original text, which is considered biased, and the ground truth label, which is a debiased test that we have in the instruction data set. And then we apply a different model to debias the text. For example, Llama 2 7B base model, Mistral base model, and then prompt tune them, and finally our model. And then we again calculate all these metrics. So if you see from original data to the ground truth label, definitely there is a lot of reduction in the bias and toxicity. And the knowledge retention is also some value which are considered to be good. In the original sentence, we see NA for the knowledge retention faithfulness because in order to calculate the knowledge retention, faithfulness, answer relevancy, we must have a comparative sentence. In the original sentence, we don't have. And now I go to the post-safety intervention. The bold values are the best one. And as I mentioned earlier, the bias and toxicity lower the good, and the knowledge retention, faithfulness higher the good. So you see that the least bias and toxicity is for the Mistral 27B instruct model, the base model, which I mentioned has been safety fine-tuned with the guardrails. Our model MBIAS also has the second best score for the bias and toxicity reduction, and the gap between the Mistral 2 vanilla model and our model is very tiny. But at the cost of this, you see that we have obtained the highest knowledge retention and the faithfulness. So definitely this address our research question that while reducing the bias and toxicity to a huge percentage, more than 90%, we have retained the knowledge and faithfulness again to a higher percentage. For the other values, relevance and these things, it is 84.02 for our case, which is also very relevant and the second best. In this slide, basically, we perform the demographic analysis. So on the left, you see there are different demographic groups. For example, women, mental disability, Chinese, Asian, Native American, physical disability, and other. There are 13 groups. And this is the toxicity data set. So we feed the toxicity data set, which is considered to be toxic, obviously for the purpose of the research, has been fed into this MBIAS model. And before that, we calculated the original bias score on the toxicity data set, which is very high. You see everything is above 80 and 90. We also calculated the toxicity, but due to brevity reasons, I'm just showing this one. And after we did debias and we calculated these scores again. So you see like our NBIAS model has reduced bias to a lot extent. For example, mental disability bias is just 1.4 now from 90%. Toxicity is even 0 for the Native Americans. For some of them, you see they're a little bit above 20, and this is a research we are doing further with the later models and changing some of the strategies also. And this is also like open for the community to add on the top of this. We have obtained a large knowledge retention, faithfulness, and relevancy, and I think that's a huge win. And if you see, some of the values are even above 90 and 95%. And in the last, we also performed the human evaluation. So in the human evaluation, I will not explain each and everything, but broadly, I can show you that on the left, there is original debiased text, then we bias text, then we debias it using MBIAS, and we get the text. Our human reviewers, what they did, they evaluated it based on Likert scale. So you see in most of the rating, they are good, but at some point we find that the output length has exceeded more than expected. And in some points, it is not able to provide respectful interaction, which are just like very minor 1 or 2 cases. And this is an area for us to explore further. Our human evaluators also provided some other like insights, for example, verbosity bias. So what happened? It is observed that this model and even other large language models also, they are naturally good, they perform good when the input is long. For example, in the first input, it says woman can fix the car and a question mark. And but when the same is given in a longer way, so the debiasing is better for the longer input. So these LLMs are naturally favoring the inputs which are longer in length. And the favoritism in the model valuations. So basically what happened, if you see our pipeline, our model 1 was GPT-4 in the role of the annotator. Then we have the middle one, MBIAS, which is an open source model. And then the third one, LLM as judge, is again GPT model. The reason we put a free model in the middle one, which is the most important part of this architecture, for 2 reasons. First, we don't want the same series of the model to annotate, to debias and evaluate each other. Obviously, they will favor each other, and there are many research papers that show this. Second is that we want to make MBIAS free for research. So Mistral model is free, Llama model is free, so one can always fine-tune, upgrade them with a little fine-tuning or changes. And finally, the model drifts. So these MBIAS have been last trained on May 2024. So maybe there are some of the linguistic biases or jargons or something that may appear in the next few years or the months, but they may not be able to be captured by the MBIAS model. So this is some of the observations from our team, and we are working on that how to handle them. Conclusion. So the limitations. In the limitation, first, I think the data we have is 8,500 sample, which is good because we have a big knowledge base of the Mistral. Same somebody can use Llama. Most of the people are working on this domain using some demonstration and the samples. We have provided like around 8,500 sample of the data. However, we think this sample doesn't cover all the biases in the world. So this is definitely limitation. Subjectivity in bias is very important, and the reason is that a thing that is biased for me may not be biased in your culture or your society. So this is a very subjective bias. What we have done according to our best practices, our knowledge. We have like studied. We have from the psychological point of view, social science, computational science. But this is a very big area, and there's no one consensus on that. The second thing is the risk for further discrimination. So by showing this kind of example or giving this kind of training example, our purpose is not to hurt the sentiments of those people who have been already suffering from this kind of discrimination, but our purpose is to bring the conversation that are more inclusive for them. So these are all the things, limitations that we think are for this study. In the future, we plan to have more enhanced fine-tuning, real-time feedback from a bigger group, more coverage of the data set. Right now, we are using LLM-based evaluation. I think statistical evaluation still add a lot of value, so we will definitely want to do this. So here I end my presentation. So MBIAS is basically an instruction fine-tune model that can reduce the bias and toxicity in LLM while preserving the knowledge. And the model is robust because it has been parameter efficient fine-tuned. We had made data, code, and model available for the community's use. If there are any questions, I'm happy to answer. Thank you very much.
Thank you very much for the presentation. I had a few questions. So the first question is that it is related to the dataset design. That why did you use two formats for designing datasets?
Sorry, you're asking question?
So you mentioned that you have used two formats for designing datasets. I guess one was OpenAI and one was some other format. So why did you use two formats and not a single consistent format?
I think that's an excellent question. The reason we produce in two formats is just for interpretability case. So other than this, like for our MBIAS, if you see the code, we are using that Hugging Face format. But like, for example, if somebody want to work on the alpaca format or other, they can always do. By that, I mean, we try to just maximum facilitate the researchers. If they want to fine tune using other format, they can always do. But we have used definitely one for instruction fine tuning.
Right. Also, another thought that I had in my mind is that since you are using LLM to de-bias the prompt, and if we say that the LLMs already have these bias, so do you think that there can be a better way or a more safer way? Like I know there's a human in the loop which kind of helps if LLM adds a bias, but do you think if there is a better or more scalable way if we don't use LLM to be bias?
Yeah, I think that's a great question. So in the recent research, I have seen that people are also using the adversarial kind of prompts in order to check. I mean, these are the researchers who are testing these models, whether they still are still producing further biases, even if they are acting in the role of the debiaser. This is one thing we can always do, and we are doing currently in our research project. The second thing is that if you see these models, for example, Mistral model and lately Llama 3.1 is released, they have been further fine-tuned with guardrails and a lot of safety things. So, I mean, we can take the benefit of there a lot of training and investment they have put in the guardrail processing and in producing the safe outputs. But in spite of this, I will say there is no 100% solution or reduction. something can always come inside this. If 100, it is 100% safe. For example, we have used all the measures, perturbation test, adversarial training, even this further guardrails we had. Still, the model drifts we cannot, I think, control. By that I mean, after some time, some new biases can creep in, and this is natural because they come from the society, and then they come into the data, and these models are trained on the big corpuses of web and internet. So I think so.
Yeah, makes sense.
Mhm.
Also, have you done any studies related to multilingual biases? I guess
Mhm.
many of the types of biases that you presented, I
Mhm.
think they are more applicable in multilingual scenarios.
Mhm. I totally agree with you. Data augmentation is one of the thing. One of the person from our team is currently working on this one. They are doing basically, I mean, also testing, like converting this text into another language, and then again checking the biases on this. So this is something we are doing, but definitely we plan to make it more multilingual, especially uh, like benefiting from these original models when they themselves are very much multilingual. So we should also have a solution or device that should be multilingual.
Right.
There's a question in the chat, I think.
Hello, Assalamu alaikum, Dr. Shaina.
Hi, Assalamu alaikum. Hello.
Yes. So I have two questions. My
Mhm.
first question is about your data set. Is the
Mhm.
data set consist of single sentences, or it consists of like multiple sentences?
Mhm. This is not just single sentence. Basically, we have the news articles, so they are, you can say, like they are the paragraphs in a very clean, nice format. It's not just one sentence; they are paragraphs.
Thank you. So my second question is, when you take LLM as an annotator, you already mentioned that you take GPT-4 as the annotator. There is also a possibility that instead of using human annotators after it, you annotate a single sentence, you pass it on to, let's say, two or three different LLMs, and you get like majority voting of the label. Also, is the label binary? Like
Okay.
biased or not biased?
Mhm. Okay, so I want to clarify here that for the M-bias thing, the debiasing purpose, our label is not binary. The debiased version of the text, the news article or social media post, we call that as the label. I know this is a very big label. It's not like a binary thing. It's the debiased version. This is one thing. Second thing, for your question for the majority voting. So currently we are exactly doing this. What we did, we used a couple of LLM as annotators, not the GPT-4, but the open source, because the new one are more robust. And then, for example, if five LLMs produced, it's say, in your example, for example, this thing like the classification, if the label is biased, and the sixth one say it is unbiased, so we will take the majority voting. So this is, I think, excellent idea, and we are also doing this. If you are doing this, I think you are very much, it's a great approach, definitely.
Thank you.
Thanks. There was some question in the chat, I think. What is the agenda and how to use in daily life? I think this is definitely a slide, Ali Hasnan, I have missed in my slides. So this debiser can be used as a preprocessor. For example, if you're making a recommender system, or you're making some hiring allocation system, you're working in a bank, let's say in industry, and you want to make decision on the resources, distribution of some resources or something. This unbiased debiser can be used as a preprocessor. By that it means it can free the data from the biases, and then you use it for your specific thing. One of the use case in my mind is the news recommender systems. For example, in the news recommender system, they have been trained on the news articles, so your recommendations can be biased for many reasons. If you use this kind of preprocessor before that, it will debias it, and then you feed your de-biased text into the recommender system, the results will be definitely unbiased and more inclusive. Another question from in is, are there any standard benchmarks with respect to being unbiased for model? You mean benchmarks for the debiasing? I think like most of the work that we have seen in the state of the art, they are using very nice prompts, and this prompt tuning has been used extensively. And other than this, there are many techniques which I have mentioned one of my slides. I can share the slides definitely. So there are many techniques. I think we worked differently. The reason is that we have used instruction fine-tuning. We have basically prepared a new instruct model, which act in the role of the debiaser. Is there any more questions? I think we are good.
If you don't have any other question, I think we can conclude the session here.
Yeah, sure. Thank you.
Thank you so much. Thank you so much for your time.
Yeah, thank you. Thank you very much.
Thank you.
Bye.
Bye.